Ladies and gentlemen, welcome to today's seminar, to the live audience as well as the online audience. Today's presentation is by Vladimir Smakhtin from the International Water Management Institute, IWMI, and the title, Managing Water Resources Variability for Improved Food Security and Livelihoods. The seminar is organized by the CGIAR Research Program on Climate Change, Agriculture and Food Security, CCAFS. The coordinating unit is based here at the University of Copenhagen. We also have support for today's seminar from IWMI itself and the CGI Research Program on Water, Land and Ecosystems. Today's session is part of an ongoing series where we do online live streaming to try and dialogue about interesting topics. And I'm sure today's one is interesting as well. My shorter title for Vladimir is Taming Floods to Manage Droughts. And he's going to end up with that, I hope, how we tame floods to manage droughts. Vladimir has 30 years of experience as a researcher and a research manager in water resources, looking at global and regional water scarcity issues in relation to rural development and livelihoods. He's got a PhD in hydrology, more than 100 research publications, so he's just the right person to be talking to us today, I'm sure. The seminar will be two parts. The first 30 minutes will be from Vladimir, and then we will have a 30-minute period of questions, including from the online audience. So the online audience can chat away through the seminar at the CCAF's website, and they can send questions in. We have a moderator who will then forward the questions to me at the end of the presentation by Vladimir. So Vladimir, over to you. Taming floods to manage droughts.
Thank you very much, Bruce, and ladies and gentlemen, thank you very much for coming. It's a new experience for me to talking at the same time to the audience here and to a much bigger, I believe, audience somewhere else. I've taken a liberty to change a little bit the title of the presentation compared to what originally was announced, but just a little bit. It's Bruce is talking about just floods and droughts. I put the word variability into the title to be just a little bit more inclusive. And I would like to stress from the very beginning that I have a privilege of working with a number of brilliant and dedicated colleagues who are listed here, who are part of the team, and in a way this is a team presentation. They have contributed ideas and material to this presentation. So with that I start, and you all know, of course, that everything is relative, right? But I would rephrase it and say everything is variable too, and water as well. It can be either too little or it can be either too much. This too little and too much can be in the same place in different times, and then we're talking about temporal variability. Or this too little and too much can be obviously in different places. Obviously there are regions in the world which are much better water endowed than the others. So we're talking about spatial variability then. In the water sector in the past, the spatial variability has been dealt as an example by interbasin water transfers, and temporal variability being tackled by all sorts of storage. I will not be talking today about spatial variability a lot, although you will see some global maps. It's about managing temporal variability. So I would like to start with a few facets or faces of variability, and these are the beginning. But what does variability actually mean? Starting from the water scarcity. We in the water sector talk a lot about water scarcity. And water scarcity can be defined in different ways, like per so many liters per capita per year, and in different river basins, comparing what is available in terms of resource and what is used, so identifying the levels of water stress. or in terms of access to water, when we have physical and economic water scarcity, depending on how much water is actually present and whether there is any infrastructure which allows you to access it. Whichever way you describe water scarcity, water variability makes it worse. It's implicitly or explicitly present in there. The easiest thing to look into this, just as an example, is by the set of these two maps. The first is what you see on the left is mean annual precipitation all over the globe. Wherever you see red, it's very little rainfall. Wherever you see blue is a lot. The map on the right is the coefficient of variability of mean annual precipitation. This is the measure of how one year is different from another in terms of rainfall. And what you see is also wherever the red is, this variable. Wherever the blue is, it's less variable. So you see the similar pattern in both maps in a way. That means that wherever there is little rain, it is variable. So building on the same premise and bringing up economic dimensions of the whole thing is that water variability influences the development. It can favor or it can impede the development. And this is a very interesting graph which was produced by Brown and Lal a few years back. They looked at the connection between the variability measures, the actual precipitation, and the GDP per capita. So what you see here, and I would like to attract your attention to, particularly to the set of fat cats here, so to speak. The important part in this graph is the size of the circle. So the size of the circle determines the country's GDP. So this grayish-looking group actually sits in the moderate mean annual precipitation range. It has a low coefficient of variability between months, and it is gray because it has a low coefficient of variability between years. So it's just another way of showing two different types of variabilities. So what you see here is the message from here is that a climate with moderate annual rainfall and its low variability favors prosperity. Of course, there are exceptions, but those are probably Gulf states. They sit in a very low mean annual precipitation, very highly variable rainfall, but they have a relatively high GDP. They have oil, not water. So, building on the same premise, looking into the aspects of economics of floods and droughts, those are actually recurrent and very significant disasters. They are on ends of variability, on extreme ends of variability. There is quite a number of people killed every year by floods and droughts. Blue bars are showing the characteristics for floods, and the red is for droughts. So the average number of people over this period killed in both is in the range of tens of thousands. So how does that compare to anything else? Well, the approximately 11,000 people killed every year by terrorist attacks. So that to put it into perspective. But then we have a number of people affected per year. Now we are in tens of millions. And the floods take the lion's share of people affected. Droughts a little less. How does that compare with anything? Well, we have about 33 million people living with HIV, according to 2012 information. But then now we have the economic damage per year on average in terms of floods and droughts, and you can see that floods take a lion's share of this. And now we are in billions of dollars in damage. Altogether, the total annual damage from both disasters is about $165 billion a year. How does that compare to anything? Well, the annual cost of war in Iraq and Afghanistan together over the last 10 years cost the United States about $100 billion. So we are in the right ballpark figure, so to speak. But on the other hand, wars come and go, and diseases can be cured, but floods and droughts remain, and they remain as a major natural disasters which we have been dealing with decades and hundreds of years, and we still have not resolved the issue. I would like to add also to this that 90% of all people affected by floods and droughts are in Asia, not in Europe. That floods and droughts together account for 90% of all people affected by natural disasters. Of course, there are landslides and earthquakes, etc. So those are the major problems which relates to variability of water resources and climate. And to bring you more good news, in many regions of the world, water resources variability is projected to increase with climate change. And I'm saying it not because I'm talking in the European den of SICAF's program, but it's simply because it is a real truth. This is where most of the climate scientists seem to agree. It's not just that much about cooling or warming. It is what this cooling or warming does to water resources. And how does that translate into characteristics of floods and droughts in the end of the day? So variability management floods and droughts is not a new problem, as I mentioned already, but we still have not resolved it. It must receive much more science policy and investment attention. The potential, there are estimates that by the year of 2030, the damages from floods and droughts due to climate change can increase up to $400 billion. So that's really significant, and the current damages are already exceeding all the flow from developed to developing countries. There is a number of ways in which we can deal with variability, of course, and I will not have time to go through all of them. I'd like to just show a few glimpses of what we're doing at the International Water Management Institutes in terms of looking into new ways of managing the variability. And that will be about better quantification of variability hotspots, droughts and floods, risk analysis of this and extent of these events, a rethinking of water storage. We have been damming our rivers for a long time, but whether we have done it in the right way or maybe there are other ways, this is something that I will also touch a little bit. And conjunctive management of floods and droughts for river basins through subsurface solutions. So there is a dichotomy here. First of all, conjunctive management of floods and droughts in the same place. The second is about surface versus subsurface solutions. For in the past, major effort of water sector have been on managing variability through surface solutions. The first thing to do to improve our ability to manage variability and floods and droughts, catastrophic floods and droughts in particular, is to identify and quantify hotspots of floods and droughts. What we recently did, we split the world into a number of grid cells of 100 kilometer by 100 kilometer, and we assembled the data from 6 different global databases about floods and simply counted the number of catastrophic floods in each cell. And if there is more than, over the last 110 years, if we find that in a cell, in a grid cell, there is more than 5 catastrophic floods, then that becomes a hot spot, and if it's more than 10, then it becomes a really very, very hot spot. So the reason I'm showing the Southeast Asia on the side is that because this has been our recent focus. So then what you can do with this, and then you overlay this information on the on global data sets like different cropland types, different land use, population density, flood exposed GDP, etc. And you can already see where there's the most risky areas affected by floods and what is affected in these cells, whether it's different crops, whether it's infrastructure, whether it's settlements, whether it's a combination of those, etc. But that gives you a very general picture. So in order to arrive to detailed decisions, you need a much more specific look into things. And this is where the problem starts for us, because we actually do not, at the moment, and after all decades of investing in and looking into measuring hydrological cycle, we still measure only part of it. So we don't really know a lot about, we don't measure everything. About 50% of the world is actually measured. So we turn our attention to the remote sensing techniques, which allow us to look into the various aspects of land use, various aspects of flood inundation, etc. In this particular case, again, I'm staying with the floods. What we do, we take the remote sensing images, we clean them from clouds, and in a very sophisticated, rather sophisticated but automated procedure, we can arrive to the maps which give you the actual idea about inundation. We can do it on the 8 days basis, because that's more or less the resolution of the remote sensing publicly available data set. It will tell you how things change at the 8-day basis. In principle, that results in a number of useful products, including the frequency of inundation in a particular cell, the extent of it, and this kind of products can be used by, can target the investments, can target policies, and can be used for insurance purposes as well. Now, my second thesis here again about water storage. So the inability of a nation to regulate its water resources by different ways of storage is a key contributor to very high levels of food insecurity. And this graph that may be familiar to many of you actually shows you the case in Ethiopia. What you see is the blue is the deviation of the country-wide rainfall from the mean, and what you see as a red line is the deviation of the country-wide GDP from its mean. So one can of course argue that there is not entirely good correlation, but there is definitely a very clear consistency. Wherever the rainfall goes up, Ethiopian GDP goes up, and vice versa. And why is that? Is that because the country virtually has no water storage. There is no way that the country can regulate anything, so it's all agricultural economy. Now, of course, the similar kind of statements coming from different countries in Africa. And it can be argued that, and as it probably can be seen on this graph relatively well, that in more industrialized and food-secure countries, there is much more storage per capita than in countries in Africa, like Kenya and Ethiopia. So that, to a large degree, determines the need of the countries for better storage development. Of course, these statistics also gets distorted by a number of other factors, but there is definitely a correlation here. So what you have seen so far, however, is that all the statistics are based on the large dam storage, large reservoirs, which have their pros and cons, and you all know that there is a lot of discussions going on in the world about the need to build more dams, where to build them, what social environmental impacts do they have, etc. What we are trying to say here and what we're trying to promote through our work is that the idea of water storage continuum. We say that large dams are not just the only alternative for development. There are lots and lots of different ways of storage, and we should actually see storage as a continuum. There could be reservoirs, small and large. There can be pond and tanks. There can be aquifers, deep and shallow. There are soil moisture, it's also storage. There's natural wetlands. Yes, don't make any mistake. Whenever you build a dam or infrastructure, you affect or destroy the natural storage. And natural ecosystem can regulate the flow themselves. The deeper these storages are and the bigger they are, the more reliable they are. The more artificial these types of storages are, the more complex and more specific the access to these storage types become. And the more artificial they are, the more capital, the more environmental and social cost and management complexity these storage options entail. However, if we really want to develop our water resources in a sustainable way in river basins in the future, it is important to be aware of all types of storage. In order to do that, what we're trying to do is we try to implement all sorts of different ways how to assess the need for storage, how to assess its technical feasibility. And those are just a couple of examples. You can do it in many different ways. You can do it on the scale of a country. You can, for all purposes. You can do it at much finer scale for specific water uses. The graph on the left shows you generally all the countries and a proportion of water deficit in so-called mean or expected drought that can be satisfied by existing large dam storage. So in other words, you know more or less from observations or simulations what is the general expected normal drought. And you know how much large storage is in your country. So you can compare to what extent it is possible to cope with that kind of thing. And I'm not talking about extreme droughts here, about which devastate big territories. But what that tells you is that maybe it doesn't make a lot of sense for large countries like Russia, Canada, USA, because there's a lot of differences. But it does make sense for smaller countries, and you can see that Africa actually stands out in terms of its ability to cope with even smaller droughts. So wherever you see the more brown, then the ability to cope is very low. On the other hand, you can look at the specific type of storage and for specific uses like livestock needs, and that's where Africa becomes more important, because where a lot of pastoralism and a lot of livestock, and you can look at it at the more detailed way, in a more detailed way, at the scale of 250 meters, in the case of 100 meters cells, counting the numbers of livestock per cell, counting the number of people, population density, availability of water in the cells, and by overlaying these images, overlaying these coverages, you can establish the need for storage for livestock in this particular case. The last part of my presentation today is about conjunctive management of floods and droughts. There has been a tendency, and I think it still exists to a large extent, that floods are managed and looked into by one group of people and droughts by another. But those things, as I mentioned from the very beginning, they are actually happening in the same place, just in different times. So it makes sense to manage them together. What you see here is the cross-section of an imaginary river basin. take Asia, for example, and consider, for example, Tsao Praya river basin, where probably it's probably good to just consider Tsao Praya because I'll be talking about that. That's a river basin in Thailand, which produces significant part of the agricultural product of the country. But you have similar cases all over Asia, where you have a rather agriculturally based economy in the upstream and sort of more industrialized city downstream. What happens during the dry season, what would happen during the wet season is that if you don't have enough facilities to capture water upstream, and that's what happens with Bangkok every second, third year, it gets flooded. It gets flooded big time, and industry suffers, everybody suffers. So, but that is just under the current conditions. It's already bad. What happens if there will be climate change? Under climate change, as we spoke in the beginning, there is variability will increase, and there are projections that the rainfall will become even more heavier and more intense. So the situation will be even worse. What we try to fiddle with at the moment is the idea of underground taming of floods for irrigation. It started as a UTF, and then we added irrigation, so it can be pronounced as utify, something like beautify, unify. Unify is a good thing because it unites managing floods and droughts in the same place. So what we suggest is that during the wet season we try to capture the flood water and put it underground in the same basin using different managed aquifer recharge technologies. What then can happen, so we save the city. What then can happen during the dry season is the water which has been stored underground. We can pump it out and use it for irrigation. We can use it for additional irrigation. The water is not getting lost in the Gulf of Thailand. The water is not flooding the city. It is beneficially used for the people who live upstream, and it contributes to increased agricultural production. We recently tried to have a general desktop assessment of that concept in the Tsao Phraya Basin in Thailand, and it's published. What you see is the map of the Tsao Phraya Basin itself on the left-hand side, and this is Bangkok here, Gulf of Thailand, irrigated areas shown in green, and red is the area which is drought, which encompasses the drought-prone part. This is where mostly for recurrent flooding. The river basin has significant alluvial aquifers, which you can use for storing this water, and which is the source of water itself. What we suggest is that during certain period of time in wet years, catastrophic floods, we divert this water from the streams upstream into recharge structures using managed aquifer recharge technology, and that diffuses the flood water throughout the basin. It infiltrates, and because of the hydraulic connection in the aquifers, it is then enriches the whole aquifer. During the dry season, we can use this water by pumping it out through the wells. So the possibility is there. What we are coming up with a very, very preliminary estimates at the moment is that if we harvest water only in the very wet years, approximately 1 year in 4, we will be able to harvest about 25% of the mean annual runoff of the entire basin. But once we harvest it in 1 year out of 4, but we use this water for agriculture, every year when we don't harvest. So we use it every year. So it's a continuous process. What we estimate is there is approximately around 200 square kilometers, less or more, of land that needs to be dedicated to flood harvesting. And that's not, however, a big deal. It's only just much less than 1% of the entire river basin. This land will be forgone for use for other purposes, but this is taken care of in our economic analysis. We predict that depending on the scenario of how extensively you implement this concept, we can end up with either 65 to 270 additional hectares of irrigation that will be possible. And that's not really, to put it in the context, the current irrigated land in Thailand in total is over 400,000 hectares only. So it's not a small addition to the country's irrigation potential. We estimate that there will be approximately 150 million per year on average, to income to small farmers in cash crops. And if you take that into account, then considering that the cost of implementation in any scenarios that we tried is under $1 billion US dollars, the payback time may be as low as 7 years, but in reality it probably will be a little more than that, depending on the efficiency of the scheme itself, on how much water we can capture, etc. This is, however, a very big challenge. We do not have any analogs like this practically working in the world. The farmers' participation is critical for success of this initiative. We need government support. We need to develop a step-by-step procedures of how to implement it. We need institutional support. So we are on that challenge right now as we speak. And we do hope that this kind of approaches may be very useful as an addition to the tool of managing floods and droughts in different river basins. And that is, in fact, a solution to both floods and droughts. And that is a solution which is primarily based on subsurface technologies. During the course of this presentation, I was primarily looking at variability as a culprit. It's, and I said all nasty things about it, but I don't necessarily want to finish on that note. Variability also has very important positive implications. For example, if you want to ensure a healthy river, it is important for ecology of the river to maintain or to mimic at least some sort of natural variability. It is important to have floods, it is important to have droughts, because these natural variability aspects give cues to biota in rivers, when to spawn, when to breed, things like that. So it's important for fisheries, it's important for aquatic vegetation. It is also important even for spiritual needs of the people living in Asia. So it's not necessarily something that we can completely ignore. And it is important to maintain it for the healthy rivers. So the overall challenge here is to alleviate negative aspects of variability that I was devoting most of my presentation to, but maintain the positive side of variability. And I would like to finish on that note. In the end of the day, what we want is something like this, the picture like this, which is well watered, but not necessarily too much, tranquil and environmentally friendly. Thank you very much.
Thanks, Vladimir. So now we go into the question and answer period. For the live audience, please speak close into the microphone so that the online audience can hear. And the online audience can send in questions via Twitter or the chat box, and I will get fed them from Cecilia. I think I'll start with 2 questions from Twitter. And now the challenge is my eyesight. So the first question is from Abel Balonga, environmental scientist, consultant from Kenya, and he asks, there was recently published discovery of water in an aquifer in northern Kenya in Turkana. Do you know anything about that, and do you anticipate any challenges from this discovery? And perhaps I'll give you the second question as well, Vladimir. This is from Rachel Taylor, a doctoral student at the University of Sussex. How can practitioners stimulate development of more water storage from a bottom-up perspective?
Well, I'll take the first one first, obviously. Yes, I know about this discovery, and it is, in my opinion, a good addition to the water resources in Kenya in principle, which can be used for different sorts of water supply. I'm a strong believer overall that groundwater is the key for sustainable development in the future. So whenever it comes to play, whether in Kenya, in India, or in any other parts of the world, this is pretty much a good contribution to a sustainable water resources development agenda. The reason I'm saying this is that we still, as we all know, we still have lots of poverty all over the world, and surface water resources, when they are developed, primarily developed as a big infrastructural, through the big infrastructure, which limits access to water to poor farmers. While the nature of groundwater resource is that it is diffuse, so you don't need a lot of investment, well, compared to surface infrastructure development to provide farmers with additional water resources through groundwater. The second question was, what do practitioners do from the bottom up? Well, one of the things that we are trying to advocate here through our so-called utify or beautify concept is, in a way, it's a bottom-up approach, because we're hoping that we will be able to engage farmers themselves as a flood harvesters into this process, because without their collaboration, this concept will not fly. That's just one of these possibilities. We really think that if wherever this concept is or will be implemented, the farmers which are going to be engaged into this process needs a lot of government support, incentives, financing. So to me, this is a partially bottom-up approach as well.
Okay. Any questions from the live audience?
I like the ideas, but I'm wondering if we could get some more details on how to catch the water and put it into the ground, and how to store it there so it doesn't run further out to the sea or something like that. And also how to manage the negative effects, possible negative effects that you mentioned yourself. Put more detail on it. Thanks.
Well, I can only say that I'm not sure that the time permits me to go into all details, but I can pass you quite a lot of information, which is all published, and you can read all details there. Otherwise, it will be quite difficult to... what exactly, specifically, if you can specify something, I can answer.
Well, it's just some general... Yeah, well, it is just those three things that I would like some detail on, like, because I'm kind of familiar with the main lines, but I'm just wondering how can we actually make this work in practice?
Yeah, well, this is a very good question. This is a very fresh idea, so to speak. As you can see, they're only just about a year old. So we are developing them as we speak. If you think about the last one, for example, the combined management of floods and droughts, then we have gone through the process of identifying the key factors of this approach, like where the hydrogeology is ripe for this kind of approach, where the flood harvesters can be mobilized, the financial side of things. What we need to do also is to look at, for example, aspects of prediction, when is to harvest. Because what I didn't mention, for example, is you do know in retrospect that you can harvest every 4th year or every 5th year, for example. But that's in retrospect. The trick, for example, for successful implementation of approach is to ensure that there is an early warning system that allows you to tell, okay, start harvesting this year or start harvesting this month. So we need to look into these aspects as well. We're currently investigating this process, this concept, in not just in the Thailand, but also throughout the entire South Asia, entire Southeast Asia, and our current focus is on the Ganges River Basin in India, where what we have done is we looked at the entire basin with a very detailed spatial resolution, trying to identify the suitability areas for the implementation of this approach. Suitability areas being defined as the area which highly scored on about 12 different factors, being again hydrogeology, from the infrastructure, land use, people living, etc. And we arrived to the suitability indices, which are ranging at the moment from low to high, spread out between in different river basins. In the Ganges, for example, the purpose of this exercise is to try to revitalize what we call Ganges water machine, if you have heard about this concept. It's more or less similar concept, but does not necessarily focusing on floods per se. It is focusing on using part of the monsoon water, even if it's not just, whenever it can be captured, in some parts of the catchment, and then using it in another, revitalizing the monsoon-driven hydrological cycle of the river basin. So there is a lot to tell about this.
Okay, one other thing is if you could, I forgot to say, could you just please say your name and which department you come from when you ask a question? Any more questions? I can see you have a follow-up one, but I'll see if there's some more. Yeah.
Sorry. Peter Bjørnsen, I'm from UNEP, United Nations Environment Program. You mentioned that floods and droughts are likely to be more frequent and severe with climate change. And I guess that's based on the work of IPCC, which is at the global level. How do we make that prediction useful for the management at the basin level, or at more local spatial level? Or in another way, do you think there is a prospect for forecasting floods and droughts and the effects of climate change at a more fine resolution spatially?
Well, I guess there are two sides of the question here. The how do we make use of the existing projections? My perspective on this is that climate change, be there or not, we already have a problem. So I hate to say that, Bruce, but that's how it is. we already have a problem. We have a problem of existing variability that we need to manage. So if we can find solutions to the current status of variability, to current floods and droughts, that's already a big step forward. And if we can just reduce the existing damages of floods and droughts, say by 20%, using these technologies or anything technology at all, then it's already a big achievement. I don't know whether there is a, of course, the attempts to predict the future frequencies of floods and future frequencies in the extremity of droughts are being made in different river basins by different groups. I presume the local knowledge is important, And while global projections are important, but the local knowledge should dominate, and the local projections should dominate in the future.
So I think it was Peter. There's other questions coming in, and another one relates to exactly the same issue. Have you been following the debate on climate change impacts on extreme events? There's quite some debate. Seems like there's evidence that climate change will have impacts in some regions, but not in other regions. So I think it was related to the same thing. I don't know if you got further comments.
Yeah, I can. To my best knowledge, by now at least, despite the debate, there seems to be more agreement that variability will increase in many regions, specifically detrimentally affecting the developing countries. It would be very good if variability decreases. In fact, this would be fantastic news for developing countries like Ethiopia. And in some of our early publications about 5 years ago, we did really show that it might be the case. So the climate change is not necessarily just doom and gloom. There is possibility that some nations will win. But unfortunately, to my best knowledge, such projections are relatively rare.
Any more questions from this group? So two others that I have. So this is an exciting idea of capturing floods and managing the water. And there's two kind of questions which relate to that. So one is the fact that, and you said it yourself, that farmers' participation is critical. So, and to achieve that, you need this collective action amongst smallholder farmers. So to what extent is your research and development efforts dealing with the social issues as opposed to the technical issues? There was the one issue. And the other one was, so flood events often come with very intense rainfall events over short periods. And so to what extent can this kind of technology capture that kind of issue?
Okay, on the social side, you already answered the question. If we go the way that we're proposing, the social issues become particularly important. We can figure out all technical details probably within the comfort of our offices, but with a few exceptions. But when it comes to actually implementation of things, going into action research, then the farmers' participation is critical. What we really need with the implementation of these technologies is to set up a few pilot tests where we can have dedicated farmers and then we monitor the progress and see what happens. The schemes that I presented here, to some degree, remind of the payment for ecosystem services and benefit sharing mechanisms. You know, in principle, the urban managers, the urban centers, in order to provide incentives for flood protection, can invest some funds into the upstream development. And that's becoming the issue of a social research and implementation. Regarding the floods, which become more sort of narrow, if you like, and peaky, well, again, it has implications and connotations to both the ability of dealing with them by surface technologies and by subsurface. If you have smallish surface reservoirs, then there is the fair chance that the destructive element of floods actually will be such that it will just wash away all these small structures. When it comes to capturing the floods through subsurface means, it has also become a problem. How do you divert? How do you know when it comes? What we did during the course of this calculation is that we looked at the possibility of capturing the peak flow. We identified the biggest peak flow over the last, I think, 20 or 25 years, and we looked at how much land would be necessary to capture that peak flow. So in principle, we're looking at the issues of peak and not just something which is mean. The answer was, as I showed, that so much dedicated land is necessary to do that. I think it's all, to a large degree, is the matter of being able to predict where the flood will come, where it will go, and the location of these diversion sites, which is part of the development of the problem.
Okay. Any more questions? I'll let this group. We have one here.
My question is that you talked about that it was hard to find money for it. And I was just thinking, who are going to pay for all these technologies and all this investment in the technologies? And I'm not sure if I'm right, but I think that they get some subsidies when something is happening or a big flood in Asia and we're sending all this money to help them. But wouldn't it be better to use this money to prevent that it's happening? Mm-hmm. So I'm just thinking that it's logical that it shouldn't be hard to find money for it, because it's better preventing than just waiting for the catastrophe to happen.
Okay. And your name and your department?
Natasha Nielsen, and animal science student.
Well, thanks. That's a very good question, and it's a very right one to ask. So that I'm not sure that the audience is familiar with, but generally, every dollar you invest before the disaster strikes is worth $10 that are invested after it does. So, in principle, that is the common logic. On the other hand, still, when it comes to new technologies like this, there is, until you actually illustrate that it works, until you show it in practice, I think that it is quite a significant push and promotion should be done to make sure that it actually happens. So it's not that its money is not available, but there is always all sorts of other priorities. And we expect that we will be able to put together a very strong case for that type of technologies to development banks, for example. And that development banks will then, in turn, maybe help the governments to invest into this kind of technology, because that's how it operates. I don't know whether that answers your question.
But I guess the issue is that often it's humanitarian where the money gets invested rather than that upfront investment of $1. Yeah. Any other questions? So I'll do one from Africa Adapt. Do you think that there are security implications in the water resource management at the level of the Niger River Basin? Very specific one.
Say it again.
So, do you think there are security implications in water resource management at the level of the Niger River Basin? So, unfortunately, I'm not sure if the security is water security issues or conflictual.
There are obviously security issues. I'm not sure the security implications of the technologies that I just presented. Security issues definitely exist. We all know about them. On the other hand, there is always a possibility of security implications of any water resources development. In fact, there could be different scenarios in which the world will go in the next 50 years. And the regions will go in which it could be, for example, scenario of business as usual, as we do things now, or it can be the scenario of fragmentation, where, or it can be where nations would protect their own interests, and it could be a scenario of sustainability development, where the sustainability and environmental aspects will receive most attention. There can be a scenario of plutocracy domination where the market is first and economy first, things like that. So this is all these scenarios will definitely have their implications for water security in the world. For example, if it's a fragmentation scenario, then I presume this is where the water wars are becoming, but in principle, possible. And we were talking about water wars in the past in the water sector. To what extent it's real, it's a bit difficult to say, but it might happen. I just believe that it's not going to be the scenario in which the world will go.
So just perhaps a follow-up issue would be is, in the scenario of taming these floods, is it actually having to, multiple countries actually having to get together to make it happen, which adds a level of complexity?
Yes, it does. In the case of there would be river basins which are entirely within a country. In this case, the issues of water security and all these implications are less. But again, if it's Thailand, is maybe one thing. If it is India, where the water is a state subject, and there are certain issues between states, it may still be complex. In the Ganges River basin, where you have at least 3 countries involved, as Nepal, India, and Bangladesh, that definitely is a very complex geopolitical situation. And to manage this kind of concepts on the scale of entire river basins is an enormous challenge.
Good. So we must stop. So I'd like to thank the IWMI, International Water Management Institute, and the CGI Program of Water, Land and Ecosystems for jointly hosting this together with CCAFS. I'd like to thank Vladimir for a very interesting presentation, which we can keep on asking him some questions after the close. Just to note that our next online seminar is going to be about greenhouse gas emissions for smallholder farmers at farm and landscape level, and that's going to happen in December. You can get more information on our website about it. And thank everybody also for coming here today, and thanks to the online audience. Thank you.